Hello everyone. Today we'll be discussing the topic digital storage oscilloscope. So digital storage oscilloscope is an advanced form of CRO which can be used to read, store and display the waveforms which can be used to analyze the different circuits. You have multiple channels in DSO which can be used to compare multiple signals. Now we'll quickly go through the advantages of DSO. So they are capable of measuring signals very quickly in the order of micro or milliseconds. They can display the signals or an adjustable period of time. Multiple signals can be displayed and they can record signals for playback. They can be used to display physical quantities like pressure, vacuum temperature from the transducers which are available. They capture very fast and subtle changes that DMM or that is digital multimeter or CROs which cannot see or capture. They also show signal trends, that is increasing, decreasing, rise, fall or abnormal changes like static, hash, etc. And such signal trends also can be displayed on a digital storage oscilloscope. Now the main disadvantage of oscilloscope or digital storage oscilloscope is that you need some practice as well as experience with the operation of DSO in order to use it very smoothly and quickly. You need to have a solid knowledge of interpreting the waveforms, how to identify the waveforms, interpret the waveforms and plug and play with the different options which are available in the DSO. So depending on the brands that you use, there will be a difference in features, controls as well as display properties, so which also needs to be addressed. And there are different scopes available which may be differing from each other, so that also needs to be addressed. So basically, once you are thorough and familiar with the type of DSO that you are using, it will be easy for you to use it. So that is one of the main thing that you need to remember. You may not be able to use a DSO right away once it is there in front of you. Now the scopes can measure amplitude, maximum minimum voltages, average voltages, frequency period, duty cycle, rise and fall time of different signals. These are some of the quantities that can be measured using DSO for a basic signal. Now this is an image for or the front panel of a DSO. Here you can see that you have many controls available. So this is the power switch. Then you have a set of 5 controls available which is used to select different options. You can select one of the channel, and based on the channel that you select, so this is the channel select switch, CH1 channel 1 is selected here. So based on the channel that you select, you can now set different modes of operation, and you can go for coupling, AC coupling or DC coupling. Then you can type the trigger, set the trigger type, etc. So there are different options that you can set for a single channel. So the channels are provided here, 1, 2, 3, 4 channels are here, and you have an external trigger option also. So 1, 2, so these 4 are the buttons or knobs for adjusting the voltage levels or in y-axis control, and time period is controlled using this dial. Then you have position controls here in order to move the signal upward and downward as well as right to left. So you have such controls also available. Then coming to this top knobs, here you have a save button, and then in order to obtain the trigger, you have this entire setup for obtaining the trigger. Then here you have run and stop button in order to freeze a particular image. Then you have auto range, scope recall or save and recall, measure in order to get the average value. A help button also here. Another you have a save button, it seems auto reset button is here. So there are many options which are available, which is different from a normal CRO. So basically you are able to save the data and use it for future purposes. That is the main advantage of this DSO. Now we'll go through the block diagram of DSO. So the block diagram can be divided into 3 or 4 parts. First one is the data acquisition. Then you have a storage part, which also is associated or controlled with the help of address counter. Then you have control circuits, which is basically a microprocessor or microcontroller based circuits, which will be controlling or coordinating the entire process. And then you have a display, which is connected to the CRT. So this display circuit will be enabling or will be controlling the vertical and horizontal deflection plates to obtain the waveform on the CRT. Now the input signal is being provided here, and the data acquisition circuit consists of a buffer amplifier, a sample and hold circuit, and an ADC. Now this sample and hold circuit and ADC will be converting the analog signal to digital form. It will be here. These are converted into individual samples and it is converted into digital form, and these individual samples which are digitized are stored in the memory. And as the storage is being happening, your control circuit will be incrementing the address counter so that each digital value will be stored in a separate memory or continuous memory block. It's complete. It will go back to the initial point of the memory, starting point of the memory, and again it will rewrite whatever the signals that are already written here. That's how you can write memory. This memory will be can also be write operation also can be controlled using trigger circuit. Either the trigger can be from internal value, or you can provide an external trigger to stop saving stop storing into the memory. Now once the circuit is and the entire process is being synchronized using a sample clock from the time-based circuit. So you have a time-based circuit which gives you a reference clock. So that clock will be controlling the circuits that are there inside this control circuit block. Now once the storage is done, now you need to display signal into the CRT. Now you have 2 circuits available. One is a vertical circuit which is connected to the vertical amplifier and vertical deflection plate, and then you have a time-based counter which provides signal to the horizontal deflection plate. As in the case of CRO, this time-based circuit will be providing a base for the signal that is to be displayed. This will be generally a sawtooth waveform. You are providing with a digital to analog conversion, and those you will be getting individual data points, and these data points will be which is there in the horizontal deflection system has to coincide with the vertical deflection system. So that is being controlled using control circuit. So whenever one of the address is being accessed, it will be providing you a single unit of data. So that will be converted to a point form or an individual signal, and that will be sent to the vertical amplifier. Then the address counter will be updated to the next address counter, and you will be taking out the next data which is stored. And once the address counter is updated, automatically the time-based counter also moves. Will also get adjusted in such a way that there will be synchronization between the waveform that is there or the data that is there in the vertical circuit and the time-based circuit, and you will be displaying the data in terms of dots. So you will be getting one dot, and that will be displayed on the screen. Okay, once you get the first dot, the time-based circuit will be moving to the next step, and your DSA also will be acquiring the next data so that your next dot will be acquired. So in that way you will have a number of dots created, and time-based circuit also will be moving. It will be updated, so you will be getting a number of data points displayed on the CRT screen. So the vertical deflection plates as well as horizontal reflection plates are energized in a synchronous manner so that you are able to recreate the signal, and this will be repeatedly done, and the data will be taken from the memory. Once the single cycle is completed, again the process will be repeated for the next cycle, so that you will have an overwriting of the data points on the CRT. So the number of points that are displayed, dots which are displayed on the screen, will be so large that the signal will be ultimately looking like a continuous waveform. Okay, so that's how you get a continuous waveform with the help of a digital storage oscilloscope. Now we'll just try to decode what is there on the DSO screen. So once the signal is being displayed on the DSO screen, you'll have some certain characteristics which are displayed below that. So from that you are able to understand some information regarding the signal as well as the mode of operation of the DSO. So here you can see that yellow color is displayed here, which indicates that 1 is being shown here, which shows the channel 1, and each rectangle grid is 500 millivolt in magnitude. So this is the rectangular grid. So this is 500 millivolt, and you are using an automatic function generator, and sine wave is the shape with a frequency of 100 kilohertz, and 1 volt peak to peak is the amplitude of the transferred wave. So here you can see that 500 millivolt is there, so totally of 1 volt, and so 1 volt it is peak value 1 volt peak. So here you have 4 microsecond as the time period, horizontal time period, and you have 5 into 10 raised to 9 samples per second available. Channel 1 is used to trigger it, and the image is centered at 0 seconds from the trigger point. So it is almost in synchronization with the trigger point, and you'll have 1 million data points collected. While you display it, 1 million data points will be collected and saved into the memory location, and the triggering will be occurring when the signal is passing through 0 volt, or the rising signal is passing through 0 volt. That is, once the rising signal passes through 0 volt, increasing signal is passing through 0 volt, your trigger occurs, and that from that point you will be saving the data. Again, here you will have a trigger and you will be saving the data. So in that way you are synchronizing each cycle. So here also you will have a trigger, here also you will have a trigger. In that way you will be synchronizing the each cycle of the displayed waveform. So that is being saved in the memory. Now some of the applications that you can think of can be used to check the faulty components, can be used in medical field, radars for displaying and identifying the position of the item that is being tracked. Then it can be used to display transducer outputs like temperature, pressure, etc. It can be used to observe the VI characteristics of diodes, transistors, etc. And then electrical diagnostics of automobile engines can also be made use of this DSO, and it can be used for checking as well as repairing of electrical equipments. In medical field, you might have come across ECG, electric myogram, electric encephalogram, EEG. So such signals are displayed on this particular DSO, which can be analyzed later, saved and taken a printout and analyzed later. So such applications are there for DSO. Now we'll move on to the different probes for DSO. So DSO probe is the connecting wire which connects the circuit and the oscilloscope. So there are different types of probes available depending on the application. So we'll look into it. So what you need to ensure is that the CRO will be having a terminal, and you have to connect your probe to that particular terminal. So the input connector has to match with the connector of the scope. So you have different connectors are available, and the general ones are BNC type connector as well as SMA type connector. So these two connectors are available, which can be, and this BNC type connector you must have used in your CRO also. And the probe has to the input resistance and the capacitance of the probe has to match with the input resistance as well as capacitance of the scope. So in that way your probe will be chosen so that you will get better results. So if impedance matching is not there, that can lead to loading and such effects. Now there are a few types of probes which we are discussing: passive, active, differential as well as current probes. So first one is the passive probe. These are the most commonly used probes for general purpose measurements, and these are connected using wires and connectors, and sometimes compensation or attenuation resistors or capacitors are provided. There are no active components like transistors or amplifiers within this, and they are passive probes, and they are easy to use, relatively simple and inexpensive as well as rugged. And you will be providing some attenuation circuits in the passive probes. Attenuation is simply you are reducing the signal by some factor. If you have 10x attenuation, you will be reducing the signal by a factor of 10. That is, if your input voltage is having 10 volt, once you connect this using the probe at the CRO, you can reduce that to a level of 1 volt. So you know that you have an attenuation factor of, you have selected a probe of factor 10 attenuation, so that the signal when this multiplied with the factor will give you the actual value. So this is basically bringing the measurement signal into the limits of oscilloscope value. So if you are having a larger signal, you can use a larger attenuation factor so that you can attenuate your levels, and you can use that to display in your oscilloscope. So you can avoid damage of oscilloscope. So this can be considered as a general circuit for a passive probe. So you are providing a signal under test here, and you are having some, you can think of attenuation circuits like this. And here you can see that here you are having higher magnitude, and here your signal is having a lower magnitude, which is already attenuated, and then it is given to the scope. This is your DSO. Then active probes contain components like FETs, JFET, amplifier, and these are all active circuits, and these are generally used for taking high speed measurements, and they employ FETs which are having high input resistance and low input capacitance, which are generally recommended for applications for use in high impedance circuits, just for impedance matching, because input impedance of FETs as well as other active components are high, so you are able to match the impedance of the measured circuit as well as the probe. And these are externally powered, which can be which allows them to amplify the signals without using the power from the circuit under test. So that is one of the disadvantages of a passive probe, because it draws some power from the circuit under test. Okay, so that will lead to loading effect of the measured circuit. So here in active probes, it is externally powered so that you have minimum loading effect. So here this is your circuit for an active probe. So here you can see that a diode is being used here. You can think of you can replace this with a FET amplifier or any other amplifier, active components. You will be getting an active probe. So this is the probe end where you connect your circuit, and this is the end where you provide to the CRO or the oscilloscope. Then you have differential probes, which can be used to measure the difference between any 2 points in the circuit. They are generally used for measuring high frequency signal or signals which are having very low amplitude, just like noise, which is very random in nature. They use a differential amplifier, which you have already learned. So they'll be making use of differential amplifier to obtain a single signal which can be given to the scope input. They offer high CMMR, common mode rejection performance over different frequency range. So that is one of the advantages of differential probe. And this differential probe figure is here. So here you are applying two signals, and you have a differential amplifier here. You will be getting a single output which can be provided to the scope. The last type of probe that we are discussing is the current probe. So this is a non-invasive method for measuring electrical current. Here you can see that here is a gap available, and you're having a core provided, and this is one structure, this is a second structure. These two structures are brought together using springs, and this can be expanded. This knob can be adjusted to operate this or expand this spring outwards, just like scissors. And once you expand it, you will have an opening here, and you will be inserting your wires through this opening. So you will be entering the wires like this. You will be allowing the wires to be connected like this, and you will be closing this particular arm, and you can take the readings. So this makes use of Hall effect sensors for DC measurements as well as a current transformer for AC measurement. So here your fluke current meter is being shown. So you'll have a non-invasive measurement. You are not piercing the circuit, you are not directly coming in contact with the circuit, rather you are just allowing the wires to pass through the measuring option that is available. So this is another kind of current probe. Here you will be inserting your current wires through this particular hole. So you will be adjusting this knob in this direction so that this will be opened, and you will be inserting the wire and then you will be closing it, and then this end will be connected to the DSO. Now, how do you choose different probes? So you have to have ease of connection as well as convenience while using different probes. So different applications require different types of probes that needs to be chosen carefully, and whatever the signal that is available at the probe tip has to be faithfully replicated at the oscilloscope input. So that also need to be verified, made sure. And you should not have any signal source loading, that is the probe should not have a loading effect on the measuring circuit, that it will not draw any current from the measuring circuit that is already used. And you should have noise immunity, that is it should not allow noise to enter the measuring circuit. While you are using probe, and if you are not properly choosing the probe, you will have some noise entering into the measuring parameters, and your noise will be available at the DSO output. So that you should have a complete noise immunity while you are measuring it. So the probe needs to be chosen in such a way that it is completely free from noise issues. Now these are some of the different probing techniques that you can think of. So differential probes are generally used for most of the measurements which are not ground referred. If you don't have a ground reference, you are measuring values between 2 points in the circuit, then you should be going for differential probes. For grounded measurements, you are using single-ended probes, and if you are using higher attenuated circuits probes, you might over attenuate small signals. So that also need to be carefully chosen. So your probe attenuation has to be carefully chosen so that you are not over attenuating small signals. For low voltage signals such as ripples, 1x or 2x probe may be a better choice. So you are directly getting the output, or you are just reducing the magnitude by half. If you are using a 2x signal, you are reducing it by half. So that will be a better choice. Now if you are having any variation between scope to scope as well as from different channels on the scope, you need some compensation circuits for a particular scope channel before you use. So compensation circuits will be adjusting for any variation between the probes as well as between different scope channels for different types of oscilloscope. And the adapters, probe tip adapters that you use also has to be proper. You will have different types of adapters available, so you have to carefully choose your probe tip adapters. And your ground leads, you will have for single-ended probes you will have ground leads, so that needs to be kept short. If it is not short, long ground leads may lead to significant inductance, resulting in ringing or signal distortion. Just like noise, you will have distortion in the circuit if you are having unnecessary long ground probes. Also, long ground probes may act as antennas, picking up noise, resulting in signal misinterpretation or you'll have faulty signal displayed on the oscilloscope. So the ground leads needs to be shorted to be grounded properly in order to avoid distortion and interference of noise into the circuit. So these are some of the techniques that you need to keep in mind while you are using the DSO. Thank you so much.